we have discussed about torque on a current loop or in a magnetic field or in uniform magnetic field. That was the basic idea behind the galvanometer. In today's class, we will discuss about different types of galvanometer or moving coil galvanometer, how a galvanometer is made and what will cause the sensitivity of a galvanometer. Now we know that galvanometer is a device which can detect the presence of current in an electronic circuit. Now there are two types of galvanometer. One is suspended coil galvanometer and other one is pivoted coil galvanometer. So we will discuss the first type, that is suspended coil galvanometer. In the board you can see the diagram of a suspended coil galvanometer. The whole arrangement of this galvanometer will be kept inside a glass box. Okay, so just imagine this whole setup will be inside a glass box, and this is the setup, but this is quite huge compared to another type of galvanometer which we use in our lab. In our lab, this is not the galvanometer which we use, but this can give us more sensitive idea of the presence of current, or it can detect more value of current. So now let us discuss about suspended coil galvanometer. First of all, there is T1 and T2. These two are the screws which connect the wire. From this wire flows the current. You can see this arrow shows the direction of current. Next, this is torsion head. It is such a type of a head which can let this wire move or turn freely. Okay, if there is any force present over here, then this will not stop the wire from moving. It will let it turn freely throughout. This is a phosphor bronze strip which is very sensitive. It is connected to a concave mirror which is attached to the strip and connected to a magnet. Inside there is a core, soft iron core, which will increase the magnetic field or the presence of magnetic field. And outside there is a frame which is made up of copper coil. And this frame and the core are not attached to each other; they are not in touch. So it is kept separately. Now around there is two magnets, that is north pole and south pole of a horseshoe magnet. These two magnets provide very large amount of magnetic field. Again, the current flows through this one and passes through this T2. Now in the previous class what we have discussed is, if there is a rectangular loop in a uniform magnetic field, and if you pass a current in that loop, then it will deflect. The torque will be present over there, it will deflect, it will start moving. So now when the current starts flowing in this coil, and if there is a magnetic field, presence of magnetic field, this will start rotating. If this is kind of a rectangular copper strip, then it will start deflecting, it will start moving. And how can we detect the value of what will be the angle of rotation? We can detect with the help of this mirror. Now in front of this mirror we can keep a lamp and a scale. So the ray of light which falls over here, as it turns, the point of that light or the shadow of that light will keep on changing, and with that we can measure the value of the angle with the help of a scale. So now what happens over here is, at first when the current starts flowing, there will be a torque, or what you call is a deflecting torque. Okay, the value of the deflecting torque will be torque is equal to NIA B sin theta. This we have derived in the previous class. This is the amount of torque which will be present in this rectangular coil when the current flows in that coil. This we have already derived. N is the number of turn in the copper wire. A is the amount of current. I is the amount of current. A is the area of that copper wire. B is the magnetic field, and theta is the angle between magnetic field and the copper wire. The area of the force and the magnetic field. Now next, when a current flows in the copper wire, what happens is it starts rotating. And when it rotates, there is a wire which is attached to this copper strip. When it rotates, there will be another force which is known as restoring force. If something moves like this, there will be another force, that is restoring force, which will make it move backward. So there will be another force, that is restoring force, which is C into phi. I'll explain you what is C phi. Phi is the angle or angle of twist. Okay, how much it is twisting. Phi is the angle of twist in that strip, and C is constant, which is known as restoring torque per unit twist. Okay, this is a constant, or C is the restoring torque per unit twist. Now this is restoring force, this is the deflecting force. So there will be a point. Now first of all it will deflect, then there will be a restoring force. There will be a point when both the forces will be equal. At a point when both the forces will be equal, then this copper strip will not move further, it will be in a position of equilibrium. So there will be a point of equilibrium where restoring force and this torque or deflecting force will be equal. So NIAB sin theta will be equal to C into phi. This will be the position of equilibrium when both the force, that is restoring and deflecting, will be same. Now from here, I is equals to C phi divided by NAB sin theta. Now sin theta is the angle between this area and the magnetic field. It will keep on changing, because at first the angle will, like the magnetic field will be straight to this like this, because magnetic field is from north pole to south pole, and this is also parallel. That means this copper strip or this rectangular strip will be parallel to the magnetic field. As we move, or as current flows over here, this will start moving. That means the theta keeps on changing. So that angle is theta, and the twist in this wire will be phi. So from here, all this factor over here is a constant. So we can write I is equals to phi by sin theta, and what we can write is constant K is equals to C KAV. K is a constant, or also known as reduction factor. Okay, it's also known as reduction factor. Now from this equation, the current, it depends upon phi as well as on sin theta. That means with the change of angle, the current keeps on changing, it keeps on increasing and keeps on decreasing. Now what you have to do is you have to fix the amount of current. To make this current fixed in the circuit, what you have to do is, this can already be fixed, phi can be fixed. But what keeps on changing is this theta. So that theta has to be fixed. For that, there is a concept of a radial field. Now, we know that sin theta is maximum when sin is 90 degree. Sin theta is maximum when it is 90 degree. It is, now to make this 90 degree constant, so what we do is, instead of using a straight magnet, that is north pole and south pole, we use a type of magnet that is a cylindrical type of a magnet, cylindrical cut magnet, that is what we call. So instead of that, we use a cylindrical type of magnet like this. So magnetic field at every point will be like this. So if there is a coil over here, throughout its rotation, it will remain, the force will remain, not the angle or this area, the force will remain 90 degree with the magnetic field, only in the presence of radial field. If it is a straight cut magnet, then it will not give 90 degree. But if the angle, if the poles are like this, then at every point, the area of that strip will get a 90 degree change in the angle. Throughout this field, the angle will be 90 here, if it is 90 degree, then this becomes 1. So your I is equals to 5 or K 5. So current will be fixed, current will not be changed, it remains constant throughout. Now there are two factors known as current sensitivity and voltage sensitivity of a galvanometer. To know the sensitivity of the current, how much current it can detect and how can we increase the detection of a current, that we will learn about. For that, I will rub this equation. From this equation, phi by I, just interchanging, in place of sin theta I write 1. If we change this, what we get is, we get NAB divided by C. Okay? This factor is known as current sensitivity. Okay? Now for voltage sensitivity. For voltage sensitivity, what we know is V is equal to IR from Ohm's law, or dividing this, or we are multiplying this equation by phi. Okay, this is what we get, just multiplying with phi and doing the reciprocal. Now, in place of I by phi, in this point, what we can write is this value over here. So, in place of this, we are writing this value. So, we can write NAB divided by C into R. This factor is known as voltage sensitivity. So now, how sensitive is a galvanometer can be checked from these two equations over here. Now, the sensitivity of each of the galvanometer depends upon N, that is number of turn, area and magnetic field. Now, suppose we increase the number of turn over here. We can do that. Area, that means we can make this a bigger rectangular strip. We can also do that, and by increasing the strength of this magnet at the core, we can increase the magnetic field also. But if we keep on increasing all these things, there will be a point where we cannot do that further. It means that it will be so heavy, this device will be so heavy that it is unable to move this from one place to another. That is the biggest default or the defect which we have in a suspended coil galvanometer. It has a sensitivity up to 10 to the power minus 9 ampere. It can detect current up to this value, but because of its heavy nature, we cannot move it around. And we can also increase this factor, that is phi. Phi is a restoring torque or a constant. It depends upon the material which we use over here. So for better sensitivity, we have to take very thin wire. If we take thin wire, then what happens is, if you move around, there is a very high chance that we break the wire. So that is also a very high risk. So overall, this device gives us a better idea of the presence of current, but the problem is it will be very heavy and it is very sensitive device. It is unable to move from one place to another. So in place of this, we use another type of a galvanometer, that is known as pivoted or Western galvanometer. We'll discuss about that also. Everything in that galvanometer is similar to this one. Magnet, coil or the strap, everything is same. Only what is different is the way we check the value of or the presence of current, that is only different. So another type of galvanometer is, second type of galvanometer is pivoted or Western coil galvanometer. This is another type of galvanometer. In this galvanometer, we have got North Pole. We have got North Pole, South Pole. In the center, we have coil or iron core. Now this is connected to the scale over here. In the center it is 0. 0 means there is no current and the scale increases or decreases both sides. copper strip, which is also similar to the previous galvanometer, and this is connected to a shunt. Okay, this is perverted coil galvanometer. Everything is quite similar, but the sensitivity of this galvanometer is only 10 to the power minus 6 ampere, which is less than the other type of galvanometer. That is why we prefer the suspended coil galvanometer. But this is in a small setup which we use in the lab. We can carry it very easily. And over here, when the current flows through this coil, then it will start rotating, and there is an arrow which shows the value of the presence of current or not. If it deflects any other side, then there is a presence of current. If it is on 0, then there is no current. We have to understand that. And this is connected to a shunt. Why it is connected to a shunt? Because when the current flows, there is a high chance this device or the copper wire will start getting heated up. It will get heated up, and there is high chance that this wire can break. So the maximum amount of the current flows through this shunt. So when the current flows through this shunt, then what happens? The device is safe and we can handle it properly. So there is no damage of the device and all. So this galvanometer, about this galvanometer, I'll discuss in the class or in the lab itself while doing the practicals. But for theoretical purpose, another type of galvanometer, that is suspended coil galvanometer, and theory of that, working of that is more important. So now, the galvanometer can be converted into ammeter as well as voltmeter. That we will be discussing in the next class. Till then, please do refer to this diagram from the book itself, and those diagrams and workings are also very important for examination. This much for today. Thank you.